Okay, so finally we want to explain why this is the same formula that we got before. So recall number alpha is f dx plus g dy. So that means that d alpha is negative df dy plus dg dx wedge dy. And this is because, right, d alpha is df wedge dx plus dg wedge dy, and only the derivative of f in terms of y will survive because you can't have two dx's. Similarly, only the derivative of g in terms of x will survive. Okay, so then d alpha of vw ought to be negative df dx plus df dy plus dg dx times the determinant of v1, v2, w1, w2, because this is dx applied to, the first row is dx applied to v and w, and the second row is dy applied to v and w. And then what we end up getting is negative df dy times v1, w2 minus w1, v2 plus dg dx times the same thing, v1, w2 minus w1, v2. And then if I go up and look at the formula that I've gotten, what I end up seeing, so I've got a, let's see, I've got a df dy times v1 w2, and here I have a v1 w2 times minus df dy. I have a w1 v2 times df dy, and then I have a v1 w2 times dg dx there, and w1 v2 times dg dx. So I get the exact same thing. And then finally, we'd like to know how to extend this formula in general. Oh, and then I guess maybe one thing to note, I can also write d alpha applied to vw is equal to v applied to alpha applied to w minus w applied to alpha applied to v. So it might be a slightly nicer way to write it down. And I'd like a general formula. Your book explains the general formula pretty well. The trick you do to get this like negative subtracting trick to get sort of the formula to work properly is a little bit complicated in higher dimensions, but in any case, in general, the general case is a generalization of this, and what you end up getting is that if I have a K-form, then what I should be doing is for each, so what I should be doing is plugging in K vectors into it, getting a function, and then I want to get a K plus 1 form, right? So then I should be considering all the directional derivatives in terms of the K plus first vector, that vector field that I'm plugging in, and I should add them up in some way that gives me the right signs when I'm thinking about the area of a K plus 1 dimensional parallelepiped. So what I should end up getting is d omega applied to v0 through vk. So when I plug in like v0 through vk minus 1 to omega, I get a function, and then consider how it varies, what its directional derivative in the direction of vk is. Do this for every single set of k vectors out of the v0 through vk, and add them all up properly with the right signs. I get the sum from I equals 0 to k of negative 1 to the I vi applied to, I suppose your book likes in all these places to use square brackets, so I should probably do that as well. Vi applied to omega applied to v0 through removing VI and then VK. So this is the general formula. Okay, so stay tuned for how to generalize this when I have non-constant vector fields.